How hard could it be to make a simple everyday object like a $6 toaster from scratch? For one person, it's impossible. Thomas found that out the hard way. He mined ore and smelted it himself. He melted down his own plastic and made his own molds. 9 months and $2,000 later, the process was not going well. Thwaites thought, if a toaster costs $6, it must be simple. But when he opened it up, he was shocked to discover that it was made up of over 400 components that came from all over the world. The nickel was dug up in Russia and refined in southern Finland. The copper was probably mined in Chile and processed in the United States or China. The iron ore was from Brazil and probably turned into steel thousands of miles away. Hundreds of engineers, designers, chemists, and other specialists had to develop each of those 400 components. They're spread across continents. They speak different languages and come from totally different cultures. Thousands of years of technological development, resources fought over in wars, and global transit logistics all came together just so you could toast some bread. I've been designing physical products for 15 years, and I'm going to show you the hidden costs these objects carry and how rocks and sludge dug out of the ground miraculously turn into the objects in your life. Now, a $6 toaster hides 400 parts. But what about something that's just one piece, like this plastic fork? It sells for $3, so it must be simple, right? Nope. The steel mold to produce this probably costs over $100,000. The 600-ton injection press that it runs on can cost 5 times that. The simpler and cheaper the object looks, the more complicated the system behind it has to be. 40 billion plastic forks are made every year, and it takes some of the best manufacturing specialists in the world to make that happen. Just to give you some perspective, in the time it took me to finish saying that last sentence, another 9,000 plastic forks just spawned into existence. But even aside from manufacturing complexity at this massive scale, the challenge starts with the plastic material itself. This fork started as crude oil. Producers had to drill miles underground to extract it. This process is very dangerous. By the way, fires and explosions are not uncommon at all. In the US alone, there were 479 fatalities related to oil extraction between 2014 and 2019. And when the supply of oil dwindles, it's not exactly a secret that countries will fight for it. This plastic fork is built on top of all that. We'll come back to geopolitics in a bit, but for now, back to the oil production. The oil is shipped to a refinery where it's boiled until it turns into vapor, and from there, the vapors go through a process known as steam cracking. It's flash heated up to 850 degrees C for only 1/10th of a second in order to break down the bigger molecules into smaller olefins. It's very important that the gas mixture is rapidly cooled down. Otherwise, it'll quickly degrade. Through the use of chemical additives and a really complicated purification process, plastic is formed into these little pellets called nurdles. And yes, that is what they're actually called, nurdles. Reaching this point, just creating the plastic nurdles themselves took some of the most sophisticated chemistry and machinery that specialists have only really mastered over the last several decades. For comparison, metal fabrication has been around since about 1200 BC. Think about all this the next time you use a plastic fork for 5 minutes and then toss it in the garbage. But having the raw materials is just the beginning. Next comes the manufacturing and endless refinement. I actually have designed small plastic utensils similar to a plastic fork, and it took us 6 months just to create a design that was ready for production. I know that sounds really slow, but believe it or not, in the product development world, that is lightning fast. There's no better illustration of the iterative process than the aluminum beverage can. This process can take centuries. Almost 200 billion cans are manufactured every single year. You could fill up this entire room with cans in just 10 seconds at the current pace of production. Every detail of this design was argued over, even the shape. Bill Hammack has a fantastic video where he talks about how even the shape of the can was not obvious at first. Like, why a cylinder? Why not a sphere or a cube? Well, a sphere uses the least metal and has no corners and therefore no weak points. But it rolls off the table. It does not pack efficiently at all, and it would be a nightmare to manufacture. A cuboid shape would pack beautifully, wasting zero space. But Hammock explains that each corner is a weak point, so you'd have to use much thicker material, which is a lot more expensive. Plus, it would be really awkward to drink from it. The cylinder is the best compromise. It has 91% packing efficiency. It's easy to drink from, it won't roll off the table when upright, and it has significantly fewer stress points. Just arriving at that cylindrical shape took a lot of thought. We take this decision for granted now because all we see is this final answer. Today, aluminum cans start out as a flat disc. It's only 0.1 mm thick, about the thickness of a magazine cover. The flat disc is slowly shaped into a shallow cup and then gradually stretched to make the walls taller and taller over multiple steps. Then they add a dome to the bottom of the can to give it even more structure and strength. The entire process from a flat disc to a formed can happens in only 1/17 of a second. From there, the stepped neck is added over 11 tiny little steps, which provides even more structure. Over time, manufacturers made the can top smaller and smaller. Shaving off millimeters of the diameter from the top of the can has allowed manufacturers to use 20% less aluminum to make a single can. According to Hammock, that 6 mm reduction in size saves at least 90 million kgs of aluminum annually. That would form a solid cube 32 mm wide. This is a reference for scale right here. Another reason the walls of the can are able to be as thin as a few sheets of paper is because the contents are under pressure. It's sort of like when you blow up a balloon. The more you inflate it, the stiffer the balloon gets, even though the balloon wall is getting thinner as it gets bigger. That's why you can literally stand on top of a full can and it won't break. But you can easily crush an empty can like it's nothing. Another problem that designers and engineers had to deal with was the fact that liquids in many beverage cans are extremely acidic. Without some kind of protective layer, a can filled with Coca-Cola can eat a hole through the aluminum after only 3 days. A plastic lining is sprayed on the inside of every single beverage can in order to prevent corrosion. And as I'm sure you remember, plastic is an incredibly complex material to manufacture. Creating plastic coatings that can handle corrosive substances like carbonated soda and energy drinks takes months of development. There are over 15,000 custom plastic coatings for every beverage out there. Sealing the contents of a container is hard enough, but it's even harder to open it up later. Early cans needed a church key opener. You'd punch one end to drink from and then the other for venting. It worked, but the whole advantage of the can is that it made beverages portable. Having a package you can take anywhere loses its value when you need to remember to carry an extra tool just to open it. At a family picnic, Malfraise forgot his opener at home. So he tried opening a can using his car bumper, or at least that's what the story said. When he finally managed to open it, the drink sprayed everywhere and created a foamy mess. Arm was fed up. So, a few nights later, he came up with an idea for a pull tab design. It didn't require any sort of tool. You just lifted and peeled. After 4 years of development, he was granted a patent for his pull tab design. But this quickly created a new problem. People would pop the tab and just throw it on the ground. Beaches and parks would fill with sharp metal tabs. Fish and animals swallowed them. Many beachgoers were even cutting their feet on them. It was a major environmental issue. By the late 1970s, there were billions of cans being manufactured every year, which meant billions of loose pull tabs. People were getting fed up. So around 1960, Coors Brewing Company developed the tab that is commonly seen today, which stays attached to the can. Once again, this seems simple, but I promise you, it isn't. The opening is designed to tear open at a very specific force. It's easy for a finger, but it's strong enough to survive shipping and stacking. If you get that balance wrong, you either can't open it, or thousands of them accidentally burst open while shipping. Now, don't get me wrong, it's not a perfect design. I always hate how liquid puddles around this lip right here. Maybe someone will figure that out. The bigger point is that every rib, radius, and tenth of a millimeter is the work of thousands of specialists over several years. For centuries, people have been working to solve the problem of easily transporting food and beverage without letting it spoil. Things really accelerated in 1795 when France's Ministry of War offered up a 12,000 franc prize to anyone who could preserve food for armies fighting far away from supply lines. This is what led to modern canning as we know it. The modern aluminum can is the latest chapter in that 200-year push. Like many technological innovations, the evolution of aluminum cans started out as a way to fuel the global war machine. Within the same year, the French war machine was not only trying to preserve food, it was reinventing writing tools. Armies run on written orders, maps, and inventories. Quill and ink were a mess in the field, so pencils became the tool of choice for combat operations. But there was one big problem for France. The best graphite on Earth came from a single mine in Bodal, England. And France was at war with England. Your enemy isn't going to sell you critical supplies. Just as a quick experiment, I'm going to break this pencil in half. Take note of how that made you feel just now. Maybe it didn't make you feel anything at all. We'll come back to this in a few minutes. So anyway, graphite was incredibly rare and the mine was running out. The British government knew they had a natural monopoly and needed to protect it. The British House of Commons even enacted a law that made graphite theft a serious felony. But people would still constantly try to steal graphite. It got so bad that the British officials would flood the tunnels between runs to stop thieves. But smugglers would still try their luck at robbing the mines, and were sometimes successful. It's wild to think that there was a geopolitical hissy fit over something that we can just buy at Walmart for 50 cents a piece. If nations are flooding mines over pencils, nothing about everyday objects is separate from politics. Governments fight over scarce materials. It's a tale as old as civilization. While it seems odd to fight for something like this, design depends on preserving these resources. Designers and engineers are constantly faced with the challenges of working through the limitations of sanctions, embargoes, and war. For decades, people tried making substitutes for Bodal graphite. They'd use low-grade graphite dust and mix it with binding agents like gum and wax. The result was scratchy lines that would tear through paper. Germany also made pencils, but France was at war with Germany too. France was also in the middle of the French Revolution. They were bordered by multiple hostile enemies. I cannot understate how chaotic the geopolitical situation was in Europe at this particular point in time. The French were not messing around, and they were going to find a way to get their pencils come hell or high water. If they couldn't change the ingredients, they were going to change the recipe. I know a pencil shortage sounds ridiculous now, but this was a very real military problem. The French Minister of War stepped in and commissioned Nicolas Jacques Key to develop a pencil that didn't rely on borrowed Dale graphite. Conti was the perfect man for this job. He was an engineer, inventor, and an artist. He understood the science as well as the importance of handfield while writing and drawing. Legend says that Conti had a workable recipe within days, and within a year, he was granted a patent for his new process. He pulverized low-grade graphite and washed out impurities. Then he blended it with potter's clay. This created a paste which was then pressed into long sticks which were dried and fired in a kiln. The pencil cores were placed in grooved wooden slats, and then the pencil tops were covered with another piece of wood and sanded down to the desired shape. 2 centuries later, we still buy Kai pencils from the same company, and almost all modern pencils use the same process today. In the present era, electric vehicle makers redesign around graphite, cobalt, and nickel access. Chemical coatings for plastic change when new regulations are passed. The objects in our lives are shaped by finite natural resources, governance, and war. When geopolitics blocks a material, design finds another way. But it gets crazier. About 70 years later, pencils were a hot commodity, and the German pencil mogul Awar was one of the biggest pencil manufacturers in the world. In spite of that, his company was losing money. I know that sounds weird, so let me explain. In the late 1800s, Germany was a rising industrial power. For centuries, Germany was just a bunch of fractured nation-states, but they were being unified by the Prussians into the German Reich. This was very unsettling to Europe and the US, so they dealt with the German threat using 3 layers: tariffs, policy, and technology. Dixon Pencil Company, the makers of the iconic Dixon Ticonderoga pencils we still use today, had a patent for machinery innovations in pencil making that brought the cost down. This patent made it impossible for anyone, including German competitors, to use the machinery. As a result, American companies were able to flood the market with inexpensive pencils. Plus, the United States imposed a 30% tariff or import tax on any German pencils coming into the US. American pencil companies weren't subject to that tariff. Because of the patents and the tariffs imposed by the government, Germany would never compete on price when it came to pencils. It's worth noting that tariffs can be used to achieve socially positive outcomes sometimes, but as a general rule, free trade is almost always better for giving you, the end customer, a wide range of choices. The American companies also leaned heavily into the Made in USA rhetoric. It was a point of national pride to buy American-made pencils. Schools, government offices, and even railways were forbidden to buy German pencils. They could only buy American ones. Even with this protectionist policy, American pencil companies were still losing money. Their only goal was to flood the market with inexpensive options. Once they put the German competition out of business, they could jack up their prices. America had won a battle, but the real war for resource availability and supply chain was still looming. With World War I approaching, things only got worse for Germany. The Germans had to pay 60 times what it would normally cost for inferior raw materials. Wages were also 10 times as high. AWAR protested the tariffs through appeals court and usually lost. And in 1917, the Alien Property Board for the United States seized Faber's factory. It was sold to American interests. Faber made a superior product at a lower price and still lost money. Because it's never just about the product. It's about materials access, tariff walls, patent fences, nationalist procurement, and wartime seizures. When you write a shopping list with a pencil, what you're seeing is the end of a long international negotiation. Remember that pencil I broke earlier? If breaking that feels even a little bit wrong now, that's good. It means you understand what a pencil really represents. But don't feel too bad. I just have 2 smaller pencils instead of 1 big one, so not much was really wasted. But anyway, using government policy to impact markets has never stopped. Through tariffs and regulation, Chinese electric car companies are forbidden from selling lower-priced, high-quality electric vehicles in the US. Companies like Amazon and Uber operate at a loss for years or even decades on end. Supported by venture capital and lobbying government for favorable policy, they choke out the rest of the market, and once they're the last company standing, they set the terms. Of course, policy and legislation aren't just things companies use as a weapon on each other, smartphones being a great example. There are 7.4 billion of them on Earth right now, and they can be very dangerous if left unregulated. The battery in your phone is essentially a highly flammable controlled chemical fire waiting to happen. Under the wrong conditions, defective phones have exploded. Laws preventing explosions is really just the bare minimum though. The FCC caps radio exposure at 1.6 watts per kilogram to keep users safe from harmful radiation. Phones also have to be tested to ensure they don't cause radio interference with emergency services, the military, or air traffic control. Now, to be clear, these regulations make it way harder for new companies to break into the market. It's very possible that the established players like Apple or Samsung helped write some of these laws to benefit their bottom line. But it's also undeniable that these laws are a big reason why your phone doesn't just light on fire, and they're mostly successful at preventing that. Both things can be true, and even seemingly simple things have insane regulations around them. Remember that plastic fork? It has to pass FDA food contact rules to ensure it doesn't leach chemicals into your lunch. Every resin, every colorant, every additive needs to be approved before it touches your food. Although, ironically, the modern human brain might contain a plastic fork's worth of microelastics in it, but that's probably not a big deal. We're not going to worry about that. Let's just not think about that. Everything's fine. We're fine. We're fine. The point here is not that regulations are always good or always bad. The point is that policy shapes the object. The real design problem is threading those regulatory needles. Now, here's where it gets weird. You can lock down the supply chain, perfectly negotiate regulations, make a fantastic product, and still lose. The Big Mac box was a simple, brilliant fix that was doing everything right until one small but very important thing changed. Fast food is supposed to be fast. But in the early 1970s, a Big Mac was slow. McDonald's workers had to wrap the burger in several layers of packaging. The paper collar kept it from getting squashed. The foil wrap hid stains and trapped heat. And the box held everything together. Each layer had a functional purpose. But when it comes to fast food, every second counts. Now, I've designed fast food packaging before. Wasting 5 to 10 seconds wrapping every single burger starts to add up. When you have 500 orders coming in for the lunch rush, as the backlog of orders piles up, it leads to unhappy customers who get tired of waiting and staff starts to get overwhelmed. Plus, it's really hard for customers to quickly open up this packaging while they're on the go. McDonald's had to find a way to package the Big Mac in one quick motion. So in 1975, McDonald's developed the perfect solution, the polystyrene clamshell package. Now, look, I know a styrofoam box doesn't seem that innovative now, but at the time, this was like space-age tech. All you had to do was put the burger in the box, close the lid, and you were done. It did everything that the fussy paper packaging did in one simple step. Plus, the opened lid sort of functioned as a little bowl for your French fries. And the box even looked a little bit like those old-school McDonald's restaurant roofs. It was like the perfect design until it wasn't. The box didn't change, but the perception of it did. By the mid-1980s, foam packaging was considered wasteful and a threat to the environment. The CFCs used to make their foam were tied to the depletion of Earth's ozone layer. Now, McDonald's did manage to make the same styrofoam box without those harmful CFCs by 1988, but public perception stuck. The reality is that a McDonald's box was only functional for a few minutes, but the styrofoam would take centuries to biodegrade. Once people understood that reality, it was impossible to unsee the mountains of styrofoam piling up in landfills. Customers felt weird about a box that was only used for a few minutes, but would outlive them when they threw it away. Public pressure and environmental groups kept pushing McDonald's to change the packaging. And finally, in 1990, the corporation declared that they would phase out the foam packaging and return to paper. What's key here is that activism and public perception redefined the story. The rules for the packaging changed, and the design just didn't make sense in a world that was more environmentally conscious. Public acceptance and popularity is an incredibly important aspect of even the simplest objects in our lives. Now, we're almost at the end of the video, so I'm going to tell you what this is really about. Let's go back to that toaster from the very beginning. Do you know why toasters were invented? It wasn't because people needed them. A hot pan can toast bread just fine. The reason why it was made is because electrical companies needed us. In the early 1900s, demand for electricity was high at night, but demand was low during the day. Power plant generators had to spend 24 hours a day no matter what, burning expensive fuel that no one was using. So, the electrical companies hired designers to find ways to increase demand for daytime electricity. And one of the first appliances they came up with was the toaster. The toaster was not invented to give us toast. It was invented to sell us electricity. That push for perpetual growth creates artificial complexity and scarcity, layering proprietary processes and resource costs onto simple tasks that a hot pan could do just fine. But our compulsion to create and to constantly grow at all costs keeps feeding the machine until the machine becomes bigger than us. Modern industry has become a self-propelling, massive machine. All of us can influence it, but nobody can steer it. And that's the scary part. We've created a monster that moves forward on its own momentum, and that monster lurches forward in the name of progress. But nobody can even agree what progress means. That monster carries our best intentions in our most horrifyingly dangerous blind spots all at once. Each of us can see a tiny piece of this machine, but nobody can see it in its entirety. There are factors that you and I may never see and will never fully understand. And that's why these intricate objects seem so inexpensive. Someone else is paying the price. Whether they're halfway around the world or they're our future great-grandchildren, we may never see it. If the real cost of these goods was taken into account, they would be a lot more expensive, and we would treat them with more respect. So why keep building? It's because our imagination models pasts, futures, and hypotheticals. These ideas build pressure in our minds, and they have to get out. Ideas insist on entering the physical world. The urge to create is less a choice and more a deep compulsion or reflex to shape what won't leave us alone. These everyday objects are civilizational miracles. The point of Thomas Thuot's toaster project was to show us that even with modern knowledge, smelting a crude lump of metal and molding a plastic case borders on impossible without the support of other people. Self-sufficiency is an absurd delusion. There is no single human being on Earth that understands how to make any modern object completely from raw earth to finished form. Not even close. The amount of knowledge embedded in the production of a pencil is beyond any individual's comprehension. The growing of the tree requires forestry expertise. The felling of that tree requires axe handling skills. Even the creation of the axe to cut down the tree to make the pencil has its own lineage. It requires blacksmiths and woodworkers taught by someone who is taught by someone else. Every single step hides 100 more. Each of these objects is a physical record of millions of decisions by thousands of people following that compulsion to move the world a notch forward. If you listen closely, there are heartbeats inside these objects. Every component carries fingerprints. There's effort, love, and stubbornness. People who argued over a certain material, who kept notes in smudged sketchbooks, who lost sleep over a glue that wouldn't set or a blade that wouldn't cut. Their choices persist. The ghosts of their ideas live in these objects. They wash us from the silent corners of ordinary life. I made this video to honor the human chain that animates these everyday objects. Take them seriously, use them well, and waste less. These videos take hundreds of hours to make. I read 1,000+ pages of articles and books. I talk to industry experts, and I reflect on my 15 years of experience in the design industry. If you like these videos, and you want to help build a place where design and culture is discussed with depth and honesty, then consider supporting me on Patreon. You can sign up for a few dollars a month, and as a show of thanks, you get early access to my videos, plus a behind-the-scenes commentary video. I want to give a huge shout out to my patrons on Patreon. I sincerely appreciate your support. I couldn't do this without you. I hope you learned something and have a great day.